Hello and welcome to our CH461 presentation about high reliability capacitor analysis. I'm Abdulrahman Al-Sharawi and with me is Alexander Doknas for group number 16. Passive devices such as capacitors don't have a high failure rate, so they are not considered in failure analysis, especially in consumer grade type situations. However, and for the focus of this project, we're focusing on multi-layer ceramic capacitors that are especially in aerospace applications and high reliability designs. If the MLCC fails, that could cause electrical power system failure, which could fail the whole system. We wanted to look at the leading causes of failures for aerospace applications. They're basically caused by thermal cycling, but mainly elevated temperatures, increased DC biasing, and board flex, which could be caused from the missile launches. We focused on two aerospace applications, UAVs and nanosatellites, and we wanted to look at what kind of environments they experience, with UAVs experiencing elevated temperatures as well as intense vibrations, while nanosatellites go through extreme thermal cycling and also go through intensive vibrations. The most important question we wanted to ask was, does adding more capacitors to critical areas increase reliability without changing the capacitance value? Which configuration of capacitors offers the most reliability for the smallest increase in board size and cost?
So we are going to model the MLCC failure by using a Markov process. This is nice because MLCC failure is a memoryless property, so it doesn't really matter what causes the failure or how you got to that failure state. The probability doesn't change. Now, as we discovered, this isn't entirely true for capacitors because they actually do depend on a few things like bias voltage. And so if one fails, the bias voltage of the other will actually change, therefore changing the probability in the Markov process. So to mitigate that, we looked at MLCCs in particular, but we also looked at really low voltage MLCCs, less than 12 volts. And at less than 12 volts, the probability changing with like bias voltage doesn't actually change a whole lot. So be able to use just static probabilities, and then we were able to model this as a truly memoryless property and use a Markov chain, use all the wonderful tools that Markov chains bring us. We're also not looking at board flex because board flex depends on way too many variables and way too many things that we can't account for, specifically like dropping the PCB. So we'll just be looking at environmental failure, effects caused by environmental failure, specifically due from temperature and DC bias voltage. Here's our Markov chain for our capacitor failure mode. As you can see, there's three distinct failure modes: short circuit, open circuit, and value degradation. Value degradation is kind of an interesting one because there isn't any rock solid data to what value it degrades to, other than just it degrades to 90% of its original value. So we modeled this as if it hits value degradation, it still is a risk to the system and it can still fail, but it fails at the same rate as a operational no failure capacitor. Another interesting thing to note on this diagram is that a short circuit directly results in a system failure, an open circuit does not. From our Markov chain, we were able to generate a transition matrix and put this into MATLAB. MATLAB was able to generate a very nice heat map for us that allows us to look at the capacitor and how it affects the system and how it affects the system failure. And as you can see, this is pretty much what you would expect. The first few time steps that the capacitor is in the system result in a lower failure rate, and as the capacitor remains in the system and as time goes on, the failure rate is high. So we want to reduce this. You want to delay the amount of time it takes the capacitor to reach its critical failure state, and we also want to reduce the just overall failure from that one capacitor causing a system failure. So in order to generate a state transition matrix, we needed state transition probabilities, and we were able to get these from a couple of different sources. Our primary source of getting this data was from Chemet. They're a capacitor manufacturing company, and they offer engineering tools that have stuff like mean time between failure numbers and all sorts of fun stuff. So we got a whole bunch of data from different capacitor sizes, like physical sizes, so 1210 and 1206 and 0805 capacitors, and those correspond to different values of the capacitor. We also got these capacitors at different voltages, just to show that this is not a true memoryless property. But if you look at a capacitor at 3.3 volts and a capacitor at 6 volts, they're very, very similar. So we can model them even though it's not a true memoryless property. After being able to accurately model the failure modes of one capacitor using a Markov process, the next step is to see how we can increase its reliability by modifying and changing the actual Markov chain. And we can do this by just adding more capacitors in both series and parallel. And we're going to use MATLAB again to quickly get results for this. The first modification we are going to make is adding a second capacitor in parallel. This is shown here as the Markov chain. It's basically just the one Markov chain with a second branch from the operational state. And what this does is it basically just prolongs the amount of time that it sits at the open circuit failure, but not directly resulting in a system failure. So we've basically just decreased the probability of an open circuit going to a system failure. The result of this change is shown here by the MATLAB output, specifically the heat map. So as you can see, when comparing it to the single capacitor, we're not really getting that much improvement, especially in the first few time steps. So two parallel, probably not the best way to increase reliability. So for the two MLCCs in series, it's very similar to the two MLCCs in parallel. The difference here is that instead of prolonging the time it spends in the open circuit failure, we're just prolonging the time it spends in short circuit failure before causing a system failure. The MATLAB output for two MLCCs in series is very similar to two MLCCs in parallel. The only difference is that it prolongs the rate of failure for the first two states, but the overall failure rate is actually increased from two MLCCs in parallel. So this is not a recommended configuration to increase reliability either. So finally, we have decided to use two series and two parallel MLCCs together. This is the Markov chain for it. It's basically just 4 individual Markov chains. Now the difference here is that we are not only prolonging the time that it spends in the short circuit, but we're also prolonging the time it takes in the open circuit. So this should give us a really good result. The MATLAB output for the two series, two parallel configuration is as shown. We've accomplished 2 things with this. So we've increased the amount of time that it takes before that failure rate gets relatively high, and then the overall failure rate is just not as high as with either the two series or the two parallel or just a single capacitor configuration. And we've been actually able to reduce that by 70%. And this is particularly noticeable when you compare it with a single capacitor results as shown, and you can see that we've accomplished a lot with this, and we haven't actually added that many more capacitors. We've only added 3, and we've been able to greatly increase the reliability of the system.
For conclusion, what we found was that for a single capacitor, the failure rate and therefore system failure rate was significantly higher than the configuration of 2 series, 2 parallel together, while 2 in parallel or 2 in series didn't have that much an improvement over a single capacitor. This was all done thanks to Markov chains that we learned during the class. Thanks for watching our video. On behalf of myself and Alex, we would like to thank you.